Hey everybody. So welcome to today's lab. We're going to talk about light curves. All right. And this time we'll just get right to it. So light curves. In this, the students will learn about light curves, their relevance, and which characteristics they provide us from the celestial body. They will be provided with data from CTMO, the Cristina Torres Memorial Observatory, and to be able to do a basic light curve. A little bit of background. So in the previous two labs, specifically the stars and asteroids, you were able to measure the brightness of different objects using real data collected with a telescope and a CCD by calculating their magnitude. The process of measuring an object is called photometry. So photometry is something that we should be familiar with now, since we've done it at least twice. But now we have a name for those measurements that we were doing. Photometry is a technique used in astronomy that is concerned with measuring the flux or intensity of light radiated by astronomical objects. So here, the keywords, right? Flux. It's the intensity of light radiated by astronomical objects. So this light is measured through a telescope using a photometer, often made using electronic devices such as a CCD photometer. A CCD camera, like the one used in the telescope at CTMO, is in essence a grid of photometers, simultaneously measuring and recording the photons coming from all the sources in the telescope's field of view. The longer amount of time that the CCD is exposed to the light of the celestial objects, the larger the count of photons. This is called exposure time. So basically, we have this chip, and this chip is a collector of light. Each of these collectors, in this case, they're highlighting one of them, is called a pixel. So the pixel individually collects the photons, and there's some conversion that happens from photon to electricity or electrical signal, and the CCD will then convert the counts of electrons to some meaningful number. Then from there, um, this chip itself is closed, or is enclosed inside the camera itself. So whenever we take a picture, it opens, then it closes, right? So that amount of time that the sensor itself is allowed to collect light, that's the exposure time. So here, we're measuring this thing of count of photons, right? And we call that the flux. The count of photons from the CCD is then stored in a FITS file. The flexible image transport system, FITS, this is important to remember. The flexible image transport FITS is an open standard that defines a digital file format useful for storage, transmission, and processing of data. FITS is the most commonly used digital file format in astronomy. FITS files aren't just used only in optical astronomy. It's also used in radio astronomy. Spectral data is stored in the FITS format as well. In our case, it's a little bit easier to comprehend when we're talking about pictures. So here they show an example on the right side of how the FITS file is contained within itself. There's this thing called the primary header, the extension header, and then the data, which is the image itself. Now we're going to talk about photometry. Since the CCD image records the photometry of multiple objects at once, all the objects in the telescope's field of view, various forms of photometric extraction can be performed on the recorded data: relative, absolute, and differential. All three will require extraction of the raw image magnitude of the target object and a known comparison object. Right, so we could look at the raw data, right, in the three ways: relative, absolute, and differential. Where relative is when you compare one star to another. The absolute is where you only look at the value of that one star, and differential is when you're comparing you're comparing the different stars, and you're doing a difference of the raw data, right? And it might be a little much right now to try to understand, but we're actually going to practice one of these methods for this lab specifically. Um, the observed signal from an object will typically cover many pixels. This broadening is due to both the optics in the telescope and astronomical seeing. There's that word seeing. We've seen it once before, right? Seeing, where we're talking about the turbulence, right? That's created by the light having to pass through the atmosphere. Now, when obtaining photometry from a point source, the flux is measured by summing all the light recorded from the object and subtracting the light due to the sky. The simplest technique known is known as aperture photometry, and which is one of the ones that we've been doing with Aperture Photometry tool. It consists of summing the pixel counts within an aperture centered on the object and subtracting the product of the nearby average sky count per pixel and the number of pixels within the aperture. This will result in the raw flux value of the object. So this is one of the oldest techniques that has been used. If you can imagine, you have the image, right, of all the stars, and you poke a hole right where one of the stars is. If you can imagine that when you poke that hole, only the light from that star will come through. So that opening, if you know Spanish, like apertura, right, is aperture. That opening is the aperture. Now, since we have a known comparison object included in the same image, as we have been doing in the previous labs, it's possible to use it as a reference to calculate the magnitude of an unknown object by using this equation here. So here on the left side, it says it's the magnitude, magnitude 1, is equal to negative 2.5 the log of the ratio of fluxes plus plus some magnitude, right? Now, the light curve. Until now, we have calculated the brightness or the magnitude of differential or of different celestial objects, in this case stars and asteroids, in a very specific time. So we only looked at one, but this measurement can be done in time series observations. If the object changes brightness over time and you get enough data, you can plot the changes against time, and this plot is called a light curve. So this time series observation, right, is we do what we've been doing for the star or the asteroid magnitude. We do that process, but that image was only taken at one time, right? So then we take multiple images across hopefully an evenly spaced amount of time, and you just plot it: time 1, time 2, time 3, time 4, right? And as the time goes by, then we might get some change in magnitude. The magnitude might remain the same, but regardless, here is the essence of a light curve. So here's an example of an eclipsing binary system called SSRE, and here, as with an eclipsing binary system, actually we'll go into it a little bit more in detail. But here, you can see the y-axis is magnitude, and the x-axis is time. And if you look even carefully, I'm not sure if the resolution is great enough that you can pick it out, but the last name that's on the bottom of this graph is actually mine. And I was out there for this observation. I was not out there for the complete observation, but I was there for most of it. And this observation was just about 7 hours. Each little dot represents one image that was taken. And so you can definitely see that there is some kind of activity that's happening with this star system. Now, light curve photometry is measuring the variations in brightness of an object over time for the purpose of plotting and analyzing the data. The change in the brightness could be caused by different reasons, including a rotating object, for example, an asteroid, a star passing in front of another, the transit of a planet, etc. Some of the most common targets for light curve photometry include asteroids and variable stars. There's much more than the rotation rate of an asteroid to be determined by getting its light curve, including determining the size and shape of the asteroid, search for binary or other unusual asteroids, find the correlation between the rotation rate and its size, and assist in radar observations of asteroids. There on the right, you see an image of a rotating asteroid. Asteroid, in this case, is something that we could imagine like a potato shape. And if it were to be rotating like this, the profile you would see is now smaller, which means then that the amount of light that's being reflected towards us decreases. Right, so then you see the magnitude take a dip, and then as the surface area of the potato, in this case the asteroid, starts increasing, you see the magnitude also increases. And because it's rotating, you'll see that periodic motion. Now, variable stars. Variable stars are stars that change brightness. That's the definition of a variable star. The brightness changes of these stars can range from a thousandth of a magnitude to as much as 20 magnitudes over periods of a fraction of a second to years. Over, and this is important to remember, over 150,000 variable stars are known and cataloged. Over 150,000 variable stars are known and cataloged. The different causes of light variation in variable stars provide an impetus for classifying the stars into different categories. So here we broke it down just into two main types. One is intrinsic, internal changes lead the change in brightness. So intrinsic is due to internal changes, and extrinsic is due to external factors that lead to the change in brightness. So, for example, eclipsing binaries. Eclipsing binaries are made of two stars moving in orbits about a common center of mass. They are also called extrinsic variables because, for the most part, their variability is not caused by the actual changes of either of the stars specifically. Though the biggest feature on this is that you have the two stars that are shining, then one goes in front of the other and blocks the light from one star. Then, because they're orbiting around each other, allows the light to pass through, and again, blocks the light of one star. For example, here we have these algal type light curves. The algal type light curve, here we have the primary star of a system is small enough that there is a total eclipse of the primary. This causes flat portions at the deep minimums and the sharp secondary minimum. Right, so there are two dips. One is really big and the other is very small. There's the Beta Lyrae, and these stars are close to one another but not in contact. The light curve shows a notable difference in deepness between the primary and secondary minimas, and the period is longer than a day. So you see it looks very smooth and pretty evenly spread out. Compare it with the algal type. We have these very deep minimas and for the primary, and the very sharp for the secondary. Then here it looks very smooth compared to that. Now we have these their W Ursa Major group, right? So the W Ursa Major. Sometimes, because I read it, I say the W UMA. The W UMA group differs in that one or both stars have expanded beyond their Roche limit. Now, what's important for us is that the light curve periods are well under a day, sometimes less than 1/4 of a day, and have almost equal depths for the primary and secondary minima. So here, there's that example where both the minimas are relatively close to each other. So again, the same thing with this. The curve itself is very smooth, you see, compared to the algal type. But now, if we look at the beta Lyrae type and compare it with the W Ursa major group, you'll see here that there is a significant a difference in the depth of minimas. And here, there's a graphic that's showing the three different types of eclipsing binary stars that we just saw. At the very top, we see the algal type. The caption says a semi-detached binary. Now, the second one shows the beta Lyrae type, and the third one shows the W Ursa majoris type. Now, there is something very specific and important that you need to know in this lab specifically, because of the seeing. The seeing, I believe this night was a little bit bad, so that means that rather than having this very nice point source on the image, it was spread quite a bit compared to the ones that we've previously used. So here they show an image on this slide of where you need to click. So you have to click that big button that has that 5/50, and this will change your aperture size. Remember, the aperture size is the amount of, or is the size of the hole, right, that we're letting light through to see, or to measure the amount of photons that are going through that very specific spot. So rather than just talking about it, since I am already on my laptop, I can show you. So let's go to my desktop now, and I'm going to open up APT. And just give it a second. Now, when I open up APT, I found a really good example to use. This is not the image that you're using, but I'll go ahead and show you that now. So we'll go ahead and open it. And here's the deep sky image that I compiled. And actually, I think I took all of the images to make this one specifically. But you'll see the seeing on this night was not that great. The default aperture size here shows 5 pixels. That's what this button here is for. They say here, click on the big button on the right to change aperture attributes and photometry radii. This is saying the radius of the aperture is 5 pixels wide. Let's say this source. You can see the individual pixels, and you can definitely tell it's more than 5. Now, if I click on it, it'll find the centroid, or the center. Now, look at this. You see that red ring? That red ring is much smaller than the entirety of the star itself, which means that I'm losing on essential data. So what do I have to do? I have to click on the big button. When I do that, I could use this slider and change the aperture size. See, now that's getting better. That, not quite there yet. Oh, that's pretty good. It encapsulates all of it. There might be some problems if I include too much of the sky, because now I'm introducing some noise to the data. But if I were to say apply and I close it, we could actually look at the ring here in the image. See, it actually changed it. So at this point, we can see that red annulus, or the red ring that's here, which represents our aperture, is allowing all the light for that one star. Let me look at another star to use as an example. So let's move closer this way. I'll click refresh too, because you can see some funny things happened up here. So once I click refresh to, it clears the screen. All right, can I use that same aperture for this one? I don't know. Let's find out. Yeah, it might actually need to be a little bit bigger. Oh no, it seems like it captured most of it, which is the most important. If you're going to be comparing stars, you need to make sure that you compare using the same aperture, because if you're using different apertures, you have to consider mathematically a little bit different methods to be able to compare them accurately. But in our case, since the seeing in the sky is pretty much the same and the stars that I'm comparing will be about the same, then I don't have to worry about changing the aperture size after I've done it the first time. So that pretty much sums up the things that we need to do for today's lab, whichever day it is that you're doing this lab. And if you have any questions, feel free to contact me. All right. And good luck and clear skies.